Okay, so let us have another problem on the spring. So for the assembly shown, this is the assembly. We can see that there is a spring here fixed at point D, so D is not moving here. And then as a setup, if we are going to pull that 2P there, it will be stretched, wherein A will just transfer rightwards, okay? But D here is steady, or it will be on a fixed location D. A is at subject for transferring rightwards. So let us note that there is a spring constant that is equivalent to 10.2 kilonewton per meter, and it is subjected to an initial tension of 200 newton. So because of this setup, there is an initial stretch equivalent to 200 newton. So determine the force P that are applied at points B and D so that it will be directed zero point 0.6 meters away from each other. Okay, so before we are going to draw the final position of this spring setup, let us determine what is the force in the spring initially and what is the final force in the spring, because that will be the basis of our calculation of our P. So knowing that we have a spring constant, recall that spring constant K is equal to P all over delta. So this is on the provision that we first solve for the force on the spring. So if we have a value of K here given, it is implied that there is already force on the spring aside from the mentioned initial tension of 200 Newton. Now, this is the general formula for K, and it is different from the P that is defined here in the setup. So perhaps we can change this with another variable, say Fs, or the force on the spring. So substituting what we have, K is given 10.2. We can solve for factor or Fs all over the deformation on the spring, in which we can obtain this out of the geometry. So let us leave this for a while, this one. So Fs can be easily derived by cross multiplication of this 10.2 times delta S. So if we could determine delta S, then we can solve for the force on the spring. But is this really the force on the spring? It says in the problem that there is also an initial tension. So therefore, there will be, we need to add the initial tension equivalent to 200. So therefore, we can just say that the total force in spring is equal to Fs plus 200 Newton. Okay, plus 200 Newton. So next, if we are going to expand this, of course, we really need to determine delta S here, because it is the key in determining the total force on the spring. And why do we need to determine the force in the spring? Because it is our basis really to calculate P here. So let us illustrate the figure further for you to understand. Okay, so if you observe the behavior before and after, so let us have the before. This is fixed. I'll just draw a line here to indicate that this is already fixed. Okay, it will not tend to move. But A here is subject to move on rightwards direction. So after the loading, we have here. Okay, so this was stretched from A up to this. This red lines here, your spring, that is the delta of the spring, or the stretch in the spring. Okay, from here up to there. Okay. And notice that D remains to be in place. Okay, only A have transferred to certain location. Say that is A prime, okay? So from A to A prime. So here, stretchy A prime. So therefore, this is the spring deformation, okay? So the spring deformation could be calculated by simply projecting the original lines of A and D. Okay, this is the lines from A to D. Notice that these two lines covers a total of 1 meter distance because 0.5 and 0.5, that is 1 meter. So from that we can have our equation. There is a condition, the problem, that after the loading is applied, B and C, okay, let us check the problem. So okay, it just says that your B and C would be directed 0.6 away from each other. So let us label here B and C. That is B and C. So we project a line here. Okay, this yellow line here should be 0.6 so that it will just be symmetrically divided, 0.3 meters and 0.3 meters above and below. And let us note that this hypotenuse here, original length, does not change. That is equivalent to 0.5 meters. Okay, so therefore, we can now directly get this dimension, because obviously we will be having here a 3, 4, 5 triangle. See, this is the hypotenuse, 0.5. This is 0.3 here, this one. Obviously, this is 0.4 because we have a 3, 4, 5 triangle here. So we're going to place it here, 0.4 each of this dimension. So therefore, we can relate it to 1 meter, wherein this dimension delta S plus 0.4 plus 0.4 is equal to 1. So we have delta S plus 2 dimensions of 0.4. All of those shall be equal to 1. So therefore, delta S is 1 minus 0.8 meters. So it will yield to delta S is equal to 0.2 meters. So we go back to this equation, wherein we have lived a while ago. Just substitute here and then we can find the final tension in the spring. So we copy that and then we now substitute 0.2 here plus 200. Remember that 10.2 here is 10.2 kilonewton per meter. So therefore, we should multiply 1000 here. Or we can write that as 10,200 Newton per meter instead of kilonewton meters to jive it with the unit or the initial tension of 200 Newton here. So therefore, Ft here is equal to 2,240 Newton. So this is the total force on the spring considering our stretch of 0.2. Okay, out of this you can derive the force on the spring plus its initial tension, totaling to 2,240 Newton as the force total force on the spring. So what will be the use of this? We have to draw now the free body diagram of A prime. So at joint A prime, we have, say this is y and x axis. Okay. So we draw the force on the spring equivalent to 2,240 Newton. And then the identical forces here, this one, okay, AB and A prime B and AC, A prime A, A prime C, A prime B and A prime C. So this is inclined with the slope of a 3, 4, 5 triangle. So let us assume a tensile force onto this. So we take summation forces along the horizontal axis. Okay, so we can say that horizontal component of A prime B is 4/5 times A prime B plus A prime C has also horizontal component. They have similar slope. Okay, so this must be equated to 2,240. So notice that there will be two unknowns here. However, by applying this vertical equilibrium, we can just say that A prime B is equivalent to A prime C because the vertical component has the same slope of 3/5, which would eventually cancel. Hence, it is oppositely directed. So this AB is upward and AC is downward. So meaning they are just countering each other with the same magnitude. So they are just equal. So if it is equal, we can now combine this into 2. Say 2A prime B. If this is to be changed by A prime B, we multiply by this 4/5 or the common factor and just place that right term there. Okay, so A prime B would be equal to 1,400 Newton. Okay, so this is also equal to A prime C. As we have said, A prime B is equal to A prime C. So what about this 1,400? We have already determined this. That is actually the 1,400. So if we are going to finally consider joint B, we have the unknown P here, the A prime B here, that is just obtained a while ago, 1,400. Of course, if we consider equilibrium on horizontal axis, we can say that this diagonal force A prime B is also equal to BD here. Okay, they shall be equal in magnitude and both have also the same slope, that is 3 vertical, 4 horizontal, and 5 sloping hypotenuse. Okay, so by summation forces vertical, we have upward P minus 2 times 1,400, and these are just component of the vertical, and that is to be multiplied by 3/5, and those are equal to 0. So finally P is equal to 1,680 Newton. Okay, so this is the answer. So the value of P is 1,680. And the force acting on each wire is just obtained a while ago, that is 1,400. So A prime B, this one, 1,400, and this one is also 1,400. This is also 1,400, and that is also 1,400. We have seen that in joint method. Okay, so finally P is 1,680 Newton. So this is for this problem. Okay, so let us have another one. Okay, so for this problem, we have 3 springs and we're in 2 still identical steel spring are attached to this location, and then a bronze spring on the right edge of this platform hanged at 50 kilogram. By the way, this is a condition where 50 kilogram is not yet applied. So this is a condition where 50 kilogram is about to be released. Okay, so let us, of course, we need to have a conditions or distances here. So let us place the distances 1 meter and 2 meter. That is according to the problem. And the spring has its properties, the number of turns, diameter of wire, the mean diameter, and the modulus of rigidity. So we are going to compute the maximum shearing stress in each of the spring. So as usual, we are going to determine or illustrate the free body diagram and then obtain an equation. Of course, that equation would be supplemented again by the delta equation or the elastic deformation, wherein the illustration of the final geometry of the setup is being reflected, then the deformation equation will be formulated or derived from that. So let us start with the free body diagram. As for the FBD, so this is the platform. We derive the weight. Okay, so this is just a mass, 50 kilogram times 9.81 to make it a Newton weight. So we have 490.5 Newton. And of course, this should be resisted by 3 forces here. Say we have 2 P of steel and P of bronze. So we note of the distance, take note of the distance. 1 meter and 2 meter there. Okay, so we can derive an equation by taking moments at this point. Say I'll just name this as point A. So by FBD summation moments at A, we have negative P of the steel times 1 plus 490.5, the weight, the center, having a distance of 1.5 or the half of 3. Another counterclockwise, we have the bronze load times the distance 3, and that would be equal to 0. So perhaps we can arrange it transferring the constant to the right side of the equation. We have 735.75. So let this be our equation 1. Okay, there. By the way, PST here and PST on this point is not necessarily equal. So perhaps we can have a variable to indicate that these are different. Okay, perhaps we can of course just change our variable here. We have ABC variable, so that this is also B and that is C. Okay, so this is the first equation. Okay, so we still need how many equations more? 2 equations more in order to come up with the solution here. Okay, so where shall we get that equation? Of course, from the final position of this spring, and that is by elastic deformation. So let us illustrate the platform. So if we're going to pull this down, okay, there will be a slight difference on the deformation on B and C. Remember that the deformation here are not equal because it is not symmetrically placed, or the springs not symmetrically placed. So therefore, it will have more deformation at C, because this is the farthest support of the platform from the center of gravity. So therefore, there will be more deformation here at C. So illustrating that, okay, let us have deformation here. And a shorter deformation at this point. Okay, so this is the final position of our platform, where we also reflect the deformation of B. Okay, so let us label all of the deformation now. This is delta A, so that creating a flat line here. This is also delta A. Okay, delta A is present all throughout. And the whole of it is delta B. And same true with this one, this is delta C. So the excess here is delta B minus delta A, and this is delta C minus delta A. Why do we need to come up with the deformation inside this triangle? Because the triangle is so useful for us engineers. By and by we will have ratio and proportion. Okay, so we will find a triangle, and then from the triangle we usually get a relationship by ratio and proportion. So doing that, of course, we need to reflect also our dimension here. This is 1 meter and that is 2 meters. So we can relate this delta by ratio and proportion, or by similar triangles. We have delta B minus delta A is to 1. Delta C minus delta A is to 3. Okay, by cross multiplication, we have 3 delta B minus delta E is equal to delta C minus delta A. So we employ now the formula of spring deformation for each of these delta. So I think for our convenience, we first express delta in terms of its P. Okay, so delta A, for example, that is 64 PA times R cube. What is the mean radius of A? A is the steel having a mean radius of the half of 100, that is 50, with 24 turns and 83,000 modulus of rigidity, diameter of wire, that is 10 raised to 4. So this is derived from this formula of delta. So we can express delta A in terms of its actual load, 0.231 PA. Applying the same to delta B, we have 64 PB. Then copy all the remaining properties, so we come up with delta B also equal to 0.231 of PB. So finally, for delta C, we have 64 PC times mean radius of 75, 48 number of turns, and 42,000 modulus of rigidity, and 20 millimeter wire diameter. So therefore, delta C is equal to 0.193 PC. So these are the values we need to incorporate here. So delta B is this one, 0.231 PB, minus 0.231 of PA is equal to 0.193 of PC less 0.231 of PA. So of course, we need to distribute 3 here. Okay, so both has 0.693 constant. This is equal to, just copy this. Okay, so we combine terms by transposing this to the other side. we have negative 0.462 of PA, and then 0.693 of PB, less 0.193 of PC. Those are equal to 0. So this is another equation. Say the second equation obtained from elastic deformation. Okay, so we have already utilized summation moments and then elastic deformation. We still have summation forces vertical to complete the third equation. So that is easy to do. So summation forces vertical is simply the three upward forces will counter the total weight here, 490.5 newtons. So let this be our third equation. So perhaps we can leave our second equation here so that you can relate to it. So here it is. We have three equations with three unknowns. All are arranged accordingly. Okay. So starting from A, B, and then C, and then the right portion is the constant. So PA will be equal to 144.73 Newton. PB is 150.79 Newton. And then PC is equal to 194.99 Newtons. Knowing all of these three, then we can now compute for the maximum shearing stress on the spring, or the tree spring here. So we'll just apply the formula. 16 PR all over pi d cube, quantity 1 plus d all over 4r. So for the tau of PA, we have 16 times 144.73 times the radius, mean radius, 50 all over pi, wire diameter is 10. Okay, we have here 1 plus 10 all over 4 times 50. So we have spring shearing stress at A equal to 38.7 megapascals. So this is for A. Okay, and then for spring B, we have 16 times 150.79 times mean radius. So this is also steel, so we need to copy those properties. Okay, 4 times 50. So we have a value of 40.32 megapascals. So finally, tau at C is equal to 16 times 194.99 times mean radius of 75. I think we have diameter of 20 there. 1 plus 20 all over 4 times 75. So we have 9.93 megapascals. Okay, so these are the answers on this problem. So actually we have a similar, or the usual solutions on this type of problem. Just refer to the free body diagram, and then after which we illustrate the elastic deformation, and then from that elastic deformation we will form equation, and then eventually we can work on these equations to solve for the unknowns, so all of which are the formulas involving the spring deformation. So long, and have more practice at your home. Thank you.